Last time we finished building the reactor core, but somehow after 5 weeks of plasma physics, magnetic confinement, heating systems, blankets, diverters, and tritium breeding, we still haven't made any electricity. Can you guess what we're about to do? Yes, today we're building a fusion power plant. Up until now, basically our only useful output has been heat in the blanket. Calling back to episode 1, DT fusion releases 17.6 mega electron volts of energy, with 14.1 mega electron volts of that being carried away by the neutron. Since neutrons have no charge, the magnetic field doesn't really care about them. They fly out the plasma and into the blanket, where they collide with the material and lose their kinetic energy. And that energy becomes heat. Now how do we get it out of the reactor and actually do something useful with it? Different fusion power plant designs do this in different ways. So let's use Commonwealth Fusion Systems ARC design as an example. ARC plans to surround the reactor in Flibby, a molten salt made from lithium fluoride and beryllium fluoride. And this stuff is multitasking. It helps absorb and shield against neutrons. The lithium can be used for tritium breeding, like we talked about last week. It can also carry thermal energy away from the reactor. I would make another kitchen analogy here, but I prefer knuckle the Flibby. As the Flibby circulates the blanket, it picks up heat deposited by the fusion neutrons. Then that hot coolant is pumped away from the reactor into a heat exchanger, where its thermal energy is transferred into a separate power cycle. And what does this eventually heat? Water. Yeah, you really thought fusion wasn't secretly going to be boiling water? That heat produces steam, the steam drives a turbine, the turbine spins a generator, and finally, we have electricity. Amazing. Series over. Except not quite. Back in episode 1, when we talked about Q, my question was gain compared to what? Well, now we finally get to answer that question with the complete picture. The generator gives us gross electrical power, but this plant is also consuming a ton of electricity. I mean, you've seen some of the ridiculous contraptions that actually make this work. So the real equation is basically gross electricity minus everything the plant consumes equals the net electricity we can actually send to the grid. Pretty intuitive. And this is super important. A reactor can produce a ton of fusion power. It can even generate electricity and still fail as a power plant if it consumes too much of that electricity itself. And even positive net electricity isn't enough because a power plant also has to stay running. Remember all the components we put in the reactor last week? All of those are sitting in an environment with intense heat and high energy neutrons. Eventually, things wear out. And neutron exposure can also activate the reactor materials, which creates a slight maintenance problem. You can't necessarily just send me in there with a wrench. Machines like ITER are designed around remote handling systems that can remove and replace major components without directly sending people into activated areas. For a commercial reactor, this becomes incredibly important because if you build a reactor that controls plasma beautifully, mitigates disruptions, and runs autonomously for 6 months, but then takes 2 years to repair, that's a pretty shitty power plant. Experimental reactors are not production reactors. A commercial plant needs availability. Same thing happens with tritium. Last week, tritium was a reactor core problem. At power plant scale, it becomes a fuel cycle requirement. A DT power plant can't just keep buying tritium forever. That tritium self-sufficiency becomes vital for market applicability. But even with all that, it may not sound that crazy. So, why don't we have one yet? This is probably the biggest thing I learned making this series. There isn't one final fusion problem. Some of these technologies still need major improvements individually. But even if you solved every single one of them separately, you'd still have to make all of them work together at the same time inside one reliable machine. Fusion isn't waiting for one magical breakthrough. It's an enormous systems integration problem. 6 weeks ago, we started with one equation on paper. D plus T gives us helium, a neutron, and 17.6 mega electron volts. And since then, we've had to build plasma physics, magnetic confinement, heating systems, instability control, blankets, diverters, tritium breeding, cooling loops, turbines, maintenance systems, all to turn those 17.6 mega electron volts into useful electricity on the grid. Fusion itself is only the beginning. The real marvel is the stuff around it. I mean, anyone can achieve fusion. In 2018, a 12-year-old did it in his house. But after over 60 years of working on fusion, we still don't have one long-term reactor in the world. But hopefully, we'll change that soon. I hope you enjoyed Paper to Plasma, and I hope you learned a bit along the way. If ITER, Commonwealth Fusion Systems, or low-key any fusion organization is watching this, please hire me, like genuinely. As always, if you have any questions, feel free to leave them down in the comments. And please like and subscribe while you're down there. I've also been working on a hardware project this summer, so check it out here if you're interested. Otherwise, thanks for watching Paper to Plasma.